kilogram of catalyst times Kelvin. And then it's saying find T and X as functions of volume, or excuse me, catalyst weight, neglect, delta P. Okay, some other information is given. What other information do we need? Rather than me just telling you what else is given. Say it louder. Heat capacities, you're given CPA is equal to 40 joules per mole Kelvin. What else? Heat of reaction, you're given negative 20 kilojoules per mole. Do I need any other heat capacities?
Yeah, you need B's. You need B's.
Why?
Because theta is not equal to 0.
Is it not?
Well, actually, I don't know. Yes.
You're not told that you're feeding any product.
Okay.
So do I need the heat capacity of B? Anybody disagree? Can I calculate delta CP without it? No. Yeah, go ahead.
Can you figure out by saying about the H reaction?
No. I can't figure out delta CP from the delta H of reaction. I do need this, but only to figure out delta CP. So what's delta CP?
I want to know what the units of U were.
What are the units of just U?
Yeah.
Hell, man, I don't know. It's going to be
It needs to like
watt per... All right, hold
Watts
on.
per meter squared Kelvin.
no watts.
Yeah, there's going to be an area term.
Yeah. But it has to be like watts per meters to the fifth. Like, it doesn't make sense.
No, meter squared.
Meter squared.
Then it wouldn't.
And then I'm going to multiply it by meter squared, so that cancels. And then, yeah, no, the bulk density,
Oh, bulk density.
yeah.
Okay.
That answer your question? I think, yeah, it doesn't have normal density units.
Okay.
I think, but I'd have to double check. All right, I've burned through some chalk today. So what is delta CP? Do I need anything else? K, yeah. So you're given
What's that number?
3776.76. Anything else? Or do I have everything I need? All right. Energy balance.
Dr. Rubin,
Yeah.
just to clarify that term with the exponential, did you just divide the Arrhenius equation?
I don't know what you're asking.
Okay, so that equation K equals exponential.
Yes.
Divide the Arrhenius equation for that?
No.
Or that was given?
this is given, and where this comes from is how do you calculate a rate constant given a rate constant at a different temperature? That's what that, I mean, numbers have already been substituted in, but that's where that formula comes from.
Okay.
So it looks kind of like the Van Hoff, if you recognize that form in it, where it's got the, except instead of delta H, this is going to be related to the activation energy.
You can get there by taking a ratio of K's, basically, is how you would get that.
Yes. Yeah. So the A's drop out, and
Is K1 1?
Yeah.
but yeah, it's not. The only difference is that this isn't just the activation energy. This also has the other K that you're given in there.
Oh.
That's where that number comes from. Is it's. But yeah, you can derive that form pretty simply.
What's K1?
It's not given. You're just given this. I'd have to back it out from the activation energy, which is also not given. Okay, so let's do the material balance, aka design equation fun stuff. dx dw is equal to negative RA now with a prime, if we're following that notation. So that's our design equation. What's our rate equation? What's our rate equation if it's elementary?
What should the units be for the K?
I mean, they're given, but these, so if you multiply, so the concentration is going to be given now in terms of per kilogram.
Yeah, but then do those units match up?
Wait, no, that doesn't seem right. Hold on, where is that? It shouldn't be liters per second. Or it should be, hold on. Shouldn't be liters.
It would just be something like moles.
Yeah, it should be moles per kilogram catalyst. I just want to make sure it's correct or incorrect in the notes, so just give me 1 sec.
Yeah, it should be.
Yeah, he's got it in, he's got liters. It shouldn't be liters.
Isn't it first order? Should that be 1 over second? Yes.
Yeah, I don't know what's going on there. Why does he have to?
Based off that expression, how can K have any units if it's just an exponential?
No, that
There's a K1 times it. right?
yeah, the K1. K1 has to be 1.
There's some units that were here that are left over. So there's a 1 here with units. Does that answer your question?
K1 is 1.
No. It's only 1 once I've divided the number into the exponential. Guys, this is the expression for K. Right now I'm trying to figure out why the units are this way.
Shouldn't it just be per second?
Yeah, I think what this is doing is converting it from a liter, from a volume basis K to a weight basis K. That's why there's this liters per kilogram and no moles, because the moles are coming from here. So now I can use concentration in terms of moles per liter, and what do I get? It's moles per kilogram catalyst. So this is correct, because yeah, that's liters per kilogram catalyst seconds times moles per liter. And so what do I get for the rate is moles per kilogram catalyst seconds. So this is the correct units for K. It just looks odd to us because we haven't seen that many Ks with actual numbers for PBRs, evidently.
Oh.
All right, so that's our rate equation. And then stoichiometry. Concentration of A is equal to what? Let's start with the simple. Flow divided by volumetric flow rate. And what's FA in terms of conversion? Not CA naught.
A naught 1 minus x.
And then you
V
put
naught
the T,
dot
right?
1 plus epsilon.
V naught times 1 plus epsilon x. Anything else?
T over T.
P naught over P
T over
and T over T naught. Does anything simplify for this particular problem? You were told to neglect pressure drop. 1 minus x over 1 plus epsilon x. And then what do we get here? We just flip this over when we take it out of the denominator, so we get T naught over T. Okay, so the final material balance then what's epsilon for this problem?
Is it here?
1. It's pure feed, and delta is equal to 1. 1. Okay, and our energy balance? So we're going to simplify what you wrote down earlier as we go. Now this is UA over rho B, TA minus T. Negative the rate, so the rate of consumption times the negative of the delta H over